So, in last class we have discussed classical theory of Raman effect. So, there we have seen that this dipole moment, it is a dipole moment of molecules under the external radiation of frequency nu 0. So, that was sin 2 pi nu 0 t plus then it was I think alpha 0, then I think beta E 0, beta E 0 cos A minus V means 2 pi nu 0 minus nu vibration or rotation whatever t and beta E 0 cos 2 pi nu 0 plus nu vibration t. So, this dipole will oscillate with 3 frequency. So, it will emit radiation of 3 frequency, then we are telling the incident radiation of nu 0 falls on the molecules, and now it scattered by these molecules, and this scattering radiation we are getting. So, that we are getting of 3 wavelength, 3 frequency. So, these are the frequency, one is original frequency that we are generally tells the Rayleigh scattering, and additional this elastic scattering of course, and additional to frequency we are getting, that is just exactly the same by same amount, it is higher and lower than the incident frequency. So, so that is the reason origin of the Stokes and anti-Stokes lines, and that is the due to inelastic scattering, and that is the basically Raman effect. So, Raman scattering, Raman effect is basically due to inelastic scattering from the molecules. Now, here one thing is important, that what is beta I told? Beta I told is rate of change of polarizability. Okay. Beta is rate of change of polarity. Now, see, if beta equal to 0, then what we will get? There will not be these two terms, there will not be any Raman effect. Okay. So, these two term will not be there, 0, beta equal to 0. So, if there is no change of polarizability when incident radiation is falling on the molecules, then you will not get Raman effect. Okay. So, it will be Raman inactive molecule. So, it is compulsory to see the Raman effect. Okay. So, the molecule has to be Raman active. Okay. Raman active means there should be change of polarizability of the molecules when. So, this change of polarizability, so whether it will change or not. Okay. So, that if it is isotropic, okay, the polarizability that I told you, if it is isotropic, so spherical distribution of polarizability of the molecules. Okay. So, this is Raman inactive. Okay. So, in that case only this molecule will from molecule you will get the scattering, this the Rayleigh scattering, elastic scattering. Okay. So, but the polarizability, the distribution, if it is ellipsoid, okay, that means that there is a change of polarizability. Okay. So, beta is not equal to 0. So, then it is Raman active and you will get this Raman scattering. Okay. So, these two terms will exist. So, that's why we define this Raman active molecules and Raman inactive molecules. Okay. So, this same rule here, just I have taken this vibration, but this same rule is valid for the rotation. So, only this new vibration will just replace by new rotation. Okay. And this, so then you will see the effect of rotation. Okay. So, this you will get Stokes and anti-Stokes lines there. So, then that basically we tell Raman shift. What is Raman shift? What is the original incident wavelength or frequency? Now, the Stokes lines and anti-Stokes lines, it is coming just higher and lower side by this, by same amount of this, yeah, I think that we will discuss. So, this separation will depend this its separation, it will depend, it just depend by this frequency, either it's rotation or vibration. So, that I will how the spectra looks like, that I will discuss. So, this whatever this here we have considered only vibration. Now, if we the same things is valid for also rotation, and also both can be seen in both can be seen. So, then we tell this it is vibrational, and then we say this fine structure of the vibrational one. So, that because of the rotation. So, either only you can see this rotation one, only you can see the vibration one, and you can see both one in Raman spectroscopy, and in that case vibration rotation one. So, vibration one will be modulated with the rotation one, and that is the fine structure of the Raman spectra, vibrational spectra. Okay. So, now let us discuss the quantum theory. So, nowadays it is very easy, because already whatever we have discussed, the vibration and rotation, the theory we have discussed for vibration and rotation, that is only quantum theory we have discussed. So, already we know the what is the vibrational structure of the molecules, what is the rotational structure of the molecules. So, molecules have the rotational energy levels, molecules have the vibrational energy level, what are the quantum states of the molecules, okay, due to vibration, due to rotation, that already is known to us, but in that time it was not known. Okay. It was not clear picture at that time. Okay. Now, since we are quite familiar with this, so quantum theory we tell is very easy one to understand the Raman effect. Okay. It is very easy to understand the Raman effect. So, quantum theory of this quantum theory of Raman effect, quantum theory of Raman effect, okay. So, you have molecules, now molecules have this vibrational energy levels, that is already known to us, okay, or molecules have the rotational energy levels, okay. rotational energy levels. It is there in molecules. Okay. Now, incident radiation falls on it. Incident radiation falls on it. Okay. And this radiation falls on the molecules. Okay. Now, this radiation is frequency is nu 0, okay, or energy is E 0, E 0. So, when radiation falls on it, now what is radiation? Radiation is basically it is a beam of photons. Okay. So, particle nature of the radiation, it is photon is falling on it. So, this photon's energy is h nu 0, that is say E 0. Now, when h nu 0 equal to E 0, so these photons will fall on it, these photons. So, what will happen? So, these photons will be absorbed by the molecules if it matches with this particular transition. Okay. If it matches with the particular transition. Okay. So, it may happen that this incident radiation falls on it. Okay. So, it is not incident radiation is not just it's now we are considering that it consists of many photons. Okay. Now, this some photons here this molecules, okay, due to this photon it will absorb and it will go from it will be excited, it will go from one state to another state. Okay. It will go from one state to another state. Okay. So, whatever the energy E, now part of that is absorbed, del E. Okay. So, E 0 part of it is absorbed due to this, it takes the molecules from higher state to lower state to higher state, and then so for that some energy is was absorbed. Okay. Now, the rest of the radiation will have the energy say E. Okay. Now, this rest of the radiation is coming out. So, that we tell it is scattered from the by the molecules, and its energy is now lower than the incident energy. Okay. And other case may happen. So, when radiation falls on it, but now it is these molecules are in excited state. So, when radiation falls on it, so now because these molecules or this it does not stay in excited longer time. So, it come back to the down state after I think in a fraction of microsecond, it come back to the down state. Okay. So, now it will emit some additional energy, right. Now, your incident one E 0, and now from excited state to down state, these molecules have come from excited state to down state. So, you release some energy. Okay. So, that release of energy, that is del E. So, now scattered one radiation coming out. So, that one is now this energy of that one is higher than the incident one. Okay. Now, del E, and here we have whatever written. So, this we are telling this is because of it is going from one state to another state, either from lower energy state to higher energy state, okay, or from higher energy state to lower energy state. So, how much, what will be the energy of this one del E? So, del E is basically energy is this, energy is this or this or this, okay, or this, okay. So, as I told, this vibration similar for rotation also. So, what will be the this del E, what will be the del E? So, that is related with the electronic, that is related with the rotational structure or vibrational structure of the molecules, and that information basically is carried by the scattered radiation. Okay. So, so this del E is basically if that one has to find out. So, that frequency whatever nu 0, so del E by H nu, that the energy del E. So, that will be del nu, okay, del nu. So, in terms of nu 0 plus minus del nu, okay. So, del nu is nothing but this, or in terms of wave number, if you want to write, you can write this wave number. So, whatever this are, okay. So, that is the quantum theory to explain the Stokes lines and anti-Stokes lines in Raman. Now, see this Raman scattering, this Raman effect, this scattering is very weak. That is why, as I told earlier. So, that is why it was difficult to see. So, so radiation is falling, most of the radiation, 99% radiation is scattered, it is elastically scattered, okay. Only maybe 1% or less than 1% are scattered inelastically, because this probability, okay, probability to have this transition, okay, molecular this rotational or vibrational transition is very poor, okay, small, but it is there, okay, and that is why this inelastic scattered light or radiation is very small compared to the Rayleigh scattering, okay. So, this is the explanation of this quantum theory, from the quantum theory, and let us see using this quantum theory, and already it is now let us see this using quantum theory, what will be the spectral lines, Raman spectral lines for say due to the rotation, so due to the rotational motion, okay. So, as I told this del E, right, del E by H, that is basically del nu, okay. So, this already, since we know, we are familiar with the notations, energy levels, etc., in terms of wave number. So, the same thing we are writing in wave number. So, in case of rotation we know this epsilon j equal to v j j plus 1, okay, j plus 1. So, now these are nothing but this rotational energy level j equal to 0, 1, 2, 3 etc. right. Now, this due to rotational our things is a new bar of this Raman spectra, Raman spectral lines, new bar Raman spectral lines, that will be nu 0 bar incident one, then plus minus I will write that say nu bar, it is a rotational, okay, nu bar rotational, okay. So, nu bar Raman, let us write just R, okay. This will be basically we can write nu 0 bar plus minus. Now, what we can write here? This will be here, this will be basically this is coming because of transition from one rotational energy level to the another rotational energy level. So, one energy level to so I can write E j dash minus E j double dash, okay, due to this transition either going to excited state or coming from excited state to the lower state, lower energy state is coming. So, now here to get it, so we have to use selection rule. Now, selection rule for this, you know, the del j. Now, in microwave spectroscopy pure rotation, there we have seen this del j equal to plus minus 1, okay, and this different branch of spectral lines we tell depending on the depending on this j value. So, you remember that this is the I think this q, this p, this r branch, you will see different branch, okay, and then it is O and this is S, okay. So, this is I think del j equal to I think this is 0, this is plus 1, this is plus 2, this is minus 1, this is a minus 2, okay. So, these are different branch we have discussed earlier. So, here in this case here the selection rule one has to choose. So, which branch you will see, that will depend on the selection rules. So, in Raman in case of Raman effect or Raman scattering, there the selection rule is different than this one, and that selection rule is basically it is a 0 and plus minus 2, selection rule 0 and plus minus 2, okay. So, why it is so, that is again it depends, it is because of the polarizability, okay. So, whether it is ellipsoid or it is spherical, okay. In case of spherical, and it depends, so anisotropy is there. So, So, this anisotropy, because of this you see, that depends on the direction of the electric field with respect to the bond axis of the molecules. So, if electric field is applied, when it is applied in the direction of the bond axis, parallel to the bond axis, then you see this, there will be change of this, easy to change of this bond axis. So, easy to change the polarization, okay, or this polarizability. And other, if molecules are this, I think its electric field is perpendicular to the bond axis, okay, then this change of this polarization or polarizability, it's difficult in this cross direction. So, there will not be much change of this polarizability, okay. But so, it depends on the direction of the electric field and the rotation of the axis of rotation of the molecules. So, due to this polarizability, anisotropy in polarizability, so it is different, situation is different in case of Raman scattering than the original, or in microwave, what is the pure rotation we have seen, okay. So, here basically there is a effect of incident light, there incident light we have not put. In pure rotation, that is microwave spectroscopy, okay, in that case we have not put external radiation, but in case of Raman, now molecule is under external radiation, and because of that there is a change of polarizability, and this polarizability is sensitive to the direction of the electric field with respect to the bond axis, okay. So, that is why here this selection rule is different than the original one. So, that is the reason why selection rule is different. So, selection rule is del j equal to 0 plus minus 2, okay. So, when del j equal to 0, so that is basically you will get the Q branch, and you will get the Q branch, yes, and its del j equal to plus 2 and del j equal to minus 2. So, del j equal to plus 2 means you will see this S branch, del j equal to minus 2 you will see the O branch, okay. So, you will not see P and R branch in this case, okay, because plus minus 1 is not allowed in Raman scattering, okay, due to rotation. So, that is why you will see. Now, one has to here one has to consider this transition, this j dash equal to, for plus minus 1, j dash, you replace j double dash equal to j dash plus 2, okay. Okay. So, then you put here in one case b j dash plus 1 minus b j double dash plus 1, okay. Now, considering this del j equal to plus 2 or minus 2, whatever, in one case, so other one is one case plus 2, another case minus 2, okay. So, I think this way one can write, and if you put there, so you will get basically, I can write. So, two things you will get, one you will get plus, another is minus, of course, but here you will get basically you will get Q bunch, you will get S bunch, and you will get Q, S and O branch. And what will be the frequency of this, that one can I think I can just write yes, and yes, So, basically you will get, if I consider +2 means for this branch +2, if I just consider this one. So, you will get basically this part. So, nu 0 bar plus minus, you will get I think 4b, 4b, I think I have to write b, then 4j plus 6. Okay. If you consider this j del j equal to +2, so then you will get this one. Okay. And yes, so that is for S branch. Similarly, one can consider for other branch like O branch, and of course, these are Q, it is the 0. So, you will get this Raman, you will get this basically this original one, and different branch you will get for S branch, say intensity will not be same for all, anyway we are not discussing. So, you will get this branch, okay, S branch, you will get O branch. Okay. So, as a whole you will get the Raman spectra, and there is the original Q branch you will see, and then you will see S branch, you will see this R branch, not R branch, O branch, because P and R will not be allowed. Okay. So, these the Raman spectra due to modified due to the rotation. Similarly, one can see the Raman spectra for the vibration, and that I will discuss in next class. So, let me stop here. Thank you.